Hello Science Nights, welcome to really the last lesson of the Forces and Motion module. If you're watching live, it is near Christmas, so we're going to be doing how to add vectors and also road safety, because that's the IGCSE Physics difference. In my all ages lessons we were doing a Christmas lesson, but IGCSE Physics doesn't care about the seasons. So it's a bit of a mop-up lesson, right? You know how you've got the Cambridge specification and the edXL specification. So when you sit a physics IGCSE, Cambridge can have written the exam or edXL can have written the exam, and you absolutely need to know in advance before you start revising which one you're going to do, because they need you to know slightly different things. And so far, for like 13 lessons, pretty much everything we've done has been on both specifications. Like maybe it's been worded a different way. This is a lesson where we have to sort of do a little bit of mopping up, because one of them, it only wants you to learn about adding up vectors, and one of them wants you to know about road safety, and they don't cross over. So let's do both, because it's interesting. I know what you're asking. You're asking, well, which one's which, Lara? I'm doing Cambridge. Do I need to know about adding up vectors, or do I need to know about road safety? I've forgotten, okay? So you'll just have to do this whole lesson with me. Have you got a ruler with you? If you've got a ruler with you, you can do the classic activity that we in the classroom do with school children to learn about reaction time, okay? So your reaction time is how long it takes you to react to stuff. So what you would do is, it's a good way of keeping all the children in the classroom busy, because there's so many of them. One of the children holds the ruler, and the other child has both their hands open underneath the ruler, and the first child shouts "go" or something, drops the ruler, and the other child has to catch the ruler as quickly as they can. So it's a good way of kind of measuring how much ruler falls between their fingers. It's like a measure of their reaction time, right? So your reaction time is how long it takes your brain to hear the word "go" and realise that the ruler is falling and pinch your fingers together to make the ruler stop. Yeah? That's your reaction time. So obviously your reaction time is not instantaneous. It's not the speed of light. It takes a while for your brain to get going. Let's do it. Let's pretend we're in the classroom. Obviously it's not very scientific, because you know the ruler's going to drop because you're dropping it. But I'm a bit concerned about my sharp ruler. But hold your hand underneath your ruler so that your fingers are separated and the ruler's going to drop between them. And then just drop the ruler and catch it, yeah? Ugh. Surprisingly scary. Okay, so what was that? It doesn't matter. 6 centimetres. If I'd been drinking alcohol, then my reaction time would be slower. I would be more relaxed, not in a good way, and it would take me longer to react to things, okay? But I'm getting a little bit ahead of myself. Let's look at this situation when it comes to driving, reaction time when it comes to driving, because obviously this has a lot to do with road safety. There's a badger in the road. Oh, just classic. You're coming home, you're driving your car, the driver sees the badger. The driver thinks, oh, what's that? Oh, there's something up ahead. I don't know. Oh my days, it's a badger. So all the time the driver is thinking, the car is obviously moving along, okay? And we're talking split seconds here, but oh my goodness, that is actually a badger. Car keeps moving, brain whirls into gear. Oh, I'd better brake. The car keeps moving, and the driver does eventually brake. And then the car keeps moving while the brakes are applied, because obviously we know that brakes also do not work instantaneously. And finally, the car stops. Phew! Right. Could you please tell me, this is the classic thing that you need to know for your GCSE Physics, just one of them. Which bit of this situation is the thinking distance, which bit is the stopping distance, and which bit is the braking distance? I'm going to let you guess, because this is one of those bits of physics that just makes delicious sense. Like, it was just made up by humans, and it just, yeah, it makes sense. So you've got 3 arrows here. The driver seeing the badger, the driver actually applying the brakes, having been thinking about it for a bit, and the arrow where the car, showing where the car actually stopped. 3 arrows, 2 gaps between the arrows, 3 distances. What are you going to do? Draw lines if you've got this sheet in front of you from my website for free, or just think about it if you're watching the screen. Where would you put the thinking distance? What would you say the stopping distance is? And what would you say the braking distance is? Because if you haven't worked it out, then you need me to tell you. The thinking distance is just the distance that the car travels while the driver is thinking, or any object. That's nice, isn't it? Between them seeing the thing and applying the brakes. That's the thinking distance. It's the time they spend thinking about braking before they actually brake. The braking distance, I tried to mix them up to confuse you on purpose. The braking distance is the distance that the car travels while the car is braking. So the distance between the driver actually putting the foot on the brakes and the car coming to a stop. And the stopping distance is both of those added together. Isn't that nice? The overall stopping distance is the distance that the car travels in between the driver seeing a thing and the car actually stopping. And there are various things, I've already told you one of them, that affect the thinking distance and the braking distance and the stopping distance. So again, I'm not going to tell you them, I'm going to make you think about it. You've got loads of different factors here. Which of them do you think affects the braking distance, the time between the foot going onto the brake and the car actually braking? Which one affects thinking distance, the distance, I should say, between the driver seeing a thing and actually putting their foot on the brake? And one of the things that you can see here affects both thinking distance and braking distance. So your choices are speed, icy road, if the driver's tired, worn brakes, wet road, visibility, for example, if it's foggy, worn tyres, if the driver's taken drugs, and the mass of the car. And I've said I've missed out two obvious things that affect thinking distance. Can you think of them? Actually, there are lots of awareness adverts about them. Can you think of the two obvious things that I've missed off when it comes to thinking distance? And question number 3, which of those factors that I've given you affects stopping distance? I shall draw a diagram on the board while you're doing that. Oh, no, I won't. The bit of paper that I was going to use is really sticky because my office is a disaster and there were some sweets on the shelf. So I'm going to go and get a piece of paper while you do that. If you're really bored and or you're refusing to, well, if you're bored, you should just switch off. I'm not forcing you to watch this, but if you're finished or you're not doing the activity for reasons, you should like and subscribe. Yeah, do that. That'll keep you busy. What am I doing? Yeah, drawing a diagram. I've done that thing where I've completely lost track of how much time I've given you. Should we go through it? Most people on Facebook couldn't think of I told you the first one. Most people on Facebook couldn't think of the second thing. That's probably because you're not old enough to drive, so it doesn't matter. I mean, you could tell your adult off about it if you see them doing this in the car. Yeah, actually, you could. That would be a good thing for you to do. So let's go through it and I'll tell you what you should tell your adults off about if you see them doing it. Okay, well, in case you've got the sheet in front of you and you're still working, let's just go through a couple of things. First of all, did you remember what we talked about to do with momentum? Momentum, P equals mv. So momentum, P, is how difficult it is to stop something. So we've talked in previous lessons about how an elephant going slowly is very difficult to stop because its velocity might be small, but its mass is huge, massive. So it's got a lot of momentum. And the same with a bullet. Bullet's mass, very small, but a bullet is going very quickly. So it's also got a lot of momentum. It's very difficult to stop. So the same thing happens with cars, yeah? The more mass a car has, the further it's going to travel while the driver is thinking. And, well, wait, no, that's horrible science, wasn't it? Oh my goodness, not while the driver is thinking at all. Obviously, the mass of the car does not affect how far the car travels. The speed of the car affects that. The mass of the car and the velocity of the car affect the momentum, which affects the braking distance. Yeah, if you put the brakes on and you're driving a massive truck, the truck is going to go further before it stops because it's got more momentum, is what I was trying to say. Whereas if you're in a very, very small car and you press the brakes, it's going to stop sooner because it's got less mass. Is that okay? And the same with speed. If you're going really fast, it will affect the braking distance. The other thing you needed to look for in this answer was anything that reduced the friction of the road, which again, hopefully is fairly straightforward. Like cars have usually got a lot of rubber on them, rubber treads. If you take those treads off, then the car will go further because it's just skiddier, right? There's less friction pushing against it. So anything that reduced the friction, there's quite a lot of them, is also going to increase the distance that the car travels while it's braking. Like, come on, Lara, you put this PowerPoint together for a reason. So speed affects braking distance because it affects momentum. And the icy road affects braking distance because that's a friction issue. Worn brakes, again, just reducing the amount of friction on the road. Again, with the wet road, so it's more slippery, so braking distance is longer. Visibility affects thinking distance. And if the driver's tired, that also affects thinking distance. So if you can't see very well, you've just got a bit longer to think, what, is there something in the road? What is that? Holy smokes, it's a badger. Okay, and again, fairly obviously, hopefully if you're tired, then that's going to affect your reaction time. Worn tyres is another friction issue. If the driver's taking drugs, that's obviously going to cloud your thinking. And the mass of the car, we've already talked about. It's the same as sort of speed, isn't it? It gives the car more momentum, so it would make the braking distance longer. The two, I shouldn't have said obvious really. Speed is the thing that affects both of them. So that might not be really obvious that speed affects thinking distance, but obviously, because speed doesn't affect how long it takes you to think, if you know what I mean. If you think, what's that? It's a badger, and brake, you think that fast, whether the car's travelling fast or not. But obviously, if the car's travelling fast, you cover more distance while you're going, what's that? Is that a badger? Oh, I better stop. See what I mean? So the faster you're going, the more distance you travel while you're thinking. Right, the obvious thing was alcohol, which I already mentioned, and mobile phone use as well. Mobile phone use affects thinking distance because if you're on a mobile phone, you're not concentrating, it takes your brain longer to chug into gear. And did you get that that was a trick question? That all of them affect stopping distance because stopping distance is braking distance and thinking distance added together. So obviously if something affects braking distance or thinking distance, then it affects the stopping distance. Okay, right, let's move on. So that's road safety covered. What I would like you to do, please, I'm laughing because I did this lesson with my son a couple of days ago and we both made a horrible mistake here. We made different horrible mistakes. All I want you to do, right, all I want you to do is get an A4 piece of paper. It has to be A4, and just fold one of the corners down so that the short edge is lined up with the long edge, and just cut out where it meets the paper so that you get a square. Just make the biggest square that you can out of an A4 piece of paper. It's not that hard, is it? Can you even begin to imagine how my child and I both went wrong in different ways. So I'm going to do it in front of you, just in case, like me, you're really struggling. It has to be an A4 piece of paper because we're going to actually measure with rulers, and I want us to have like more or less the same measurement. So you have to use an A4 piece of paper, and you have to make it the biggest possible square you can make out of an A4 piece of paper, which is what happens if you fold a corner down like I'm demonstrating horribly on the screen. So you end up with a triangle of double paper and this single rectangle of paper on the edge. So if you've managed to do that, can you just get a pair of scissors and cut down that line so that you cut off that rectangle so that you just end up with a triangle? Yeah? It's not hard, is it? Just cut down that line. I'll do it now in front of you. How we went wrong is my child went, oh mum, look, what you can do is you could just cut parallel to that line anywhere and it works. And I was like, no, it doesn't, because we've all got to make the same size square. That's the whole point, so that the measurements work. And I know what you're thinking. How could I possibly make this mistake? I was using a piece of paper that had been folded in half already and just opened it out and just cut it down the fold. So I just ended up with 2 A5 bits of paper. Like, my life. Anyway, hopefully you have done this activity correctly and you've ended up with just a square of paper like this from an A4 piece of paper. While you're doing that incredibly difficult task, I will just do a quick recap on what, putting it there so that you understand, on what vectors are. We're adding up vectors in this lesson, and we have done that before, actually. We have done that before. First of all, very quickly, what are vectors? We've talked about this. Hopefully this isn't new news for you. You get vectors and scalars. Scalars can be described with just a number and a unit. So a distance is a scalar. You just say 5 meters or 5 miles, and that's a distance. Direction is a vector we have looked at in the past. Vectors are described with a number and a unit and also a direction. So displacement is a vector. So for example, say that someone starts here at this brown dot and they go on a beautiful long walk all around the countryside, the swirly line, and they arrive back, I don't know, in a few houses down, their mate's house next door. The distance that they travelled would just be the distance that they travelled. It would be a number and the unit that measured this wiggly line, like 10 miles. What's their displacement? Their displacement is how far they are from where they started. So in this case, how far are they from where they started? Well, I don't know, whatever that tiny little distance there is. So their displacement would just be that. And displacement is a vector, so you've got to add a direction. What direction would that arrow go in? If you're measuring the displacement from there to there, number 1 to number 2, it would be pointing towards number 2. Yeah, is that all right? So they were displaced that much in that direction overall. Is that okay? So we have actually added up vectors before, but only when both the vectors are pointing in the same direction. So we've done something like a biscuit, haven't we? And one person's pulling the biscuit in that direction with a force of 2 newtons, and one person's pulling the biscuit in that direction with a force of 3 newtons. And we've done it, it's fairly intuitive, isn't it? We've added those vectors together to look at what is the overall force acting on the biscuit. Do you remember the proper name for the overall force? The resultant force, yeah? The overall force, the resultant force, all the forces added together acting on the biscuit. So you would say, well, if that's going in that direction, that's going in that direction. Let's say it's 3 take away 2. So overall, there's a force of 1 newton acting on the biscuit in that direction. Yeah? So we've done that before. What we need to do today is look at how you add up vectors that aren't going in the same direction. They'll just be going at right angles to each other. Like that. Okay? That's what we're doing. Right. If you've managed to cut out that square, can you fold it in half 4 times? Because we need a piece of paper that has got 16 squares on it. Just with creases, you know what I mean. So fold it in half once, fold it in half twice, fold it in half 3 and then 4 times, and open out your piece of paper. And yeah, you should be able to see 16 squares marked on with little creases. There. So some of you will already know how this lesson ends, because we're going to end up looking at Pythagoras. And if you're doing IGCSE Physics, there's quite a good chance that you already know about Pythagoras, a squared plus b squared equals c squared. If you do know that, then you're going to be fine. If you don't know that, then I'm so excited that I get to teach you Pythagoras. We'll just go through it fairly quickly at the end, and then I'll set you some homework like I usually do. Okay, you got a piece of paper like that, right? I need you to use your imaginations now, children. Can you please imagine that an ant is sitting, can ants sit? I don't know, on the top left corner of your piece of paper. Now imagine that your ant walks 4 squares down and 1 square to the right. Whee, bloop. Could you please tell me, you're all with me? An ant was sitting on the top left corner of a piece of paper. It's gone 4 squares down and 1 square to the right. What distance has the ant travelled and what is its displacement, please? And can you give your answers in centimetres? Sounds very obvious, but there's never a bad time to practice measuring things. We don't actually do a lot of measuring in schools these days, really, because a lot of it is digital. So I said to bring a ruler with you. If you've got a ruler, can you just measure, because this is your piece of paper, yeah? So imagine your actual piece of paper is where the ant has travelled. What is the distance the ant has travelled? And can you measure its displacement as well? How far it is from where it started? This is why I wanted us all to be using the same bit of paper. So we'll all get slightly different answers, but hopefully not too different. Even I am like checking my ruler so many times, like, is that right? Is that right? I don't remember. Measuring things is harder than you think. Okay, I'm committing to that number. Give your answer in centimetres. What distance has it travelled in centimetres, this little ant? And yeah, what is its displacement? How far has it gone from where it started? I mean, your creases will not be terribly precise, not to get personal. So don't worry about being exact, but I want us to all be in the sort of same ballpark. Drawing in pen. I'm kind of excited about how I'm drawing in pen, because teachers would get so cross in schools, wouldn't they, including me, about people drawing. Of course you should draw in pencil, so obvious, so that you can rub it out. And no, I don't care if you've got an erasable pen, you should just draw in pencil because you can get it sharper. But I'm drawing in pen right now. If I'm taking much longer than you and you've already done it, then that means I'm being more careful than you and you've done it wrong. Shush. There's no such thing as winning in it. Well, there is, I suppose. But you don't have to go fast. 21.7. Right, I have done it. Let's go through it. So, what distance has the ant travelled? Well, it's not a trick question, right? You just measure how far it has gone on your piece of paper. So if you've used A4 paper, you should have had about 21 centimetres down and about 5.4 centimetres to the right. Actually, when I've done it here, I've got 5.2 centimetres. But roughly speaking, you just add those two different distances together and say what you've got. So you should have got about 26.4. I've got 26.3, but if you're actually measuring something, believe it or not, this is something that you might actually have to do in your IGCSE Physics, depending on which one you're doing. They might ask you to draw a scale drawing. And if you're measuring in a physics exam, they'll always give you a little bit of leeway. Like, you won't have to get the precise answer. The mark scheme will say, allow like 0.2 millimetres one way or the other way. So that's how you get the distance travelled. How did you get the displacement? Did you just draw a line from where the ant started to where the ant ended up? There's actually 2 ways to work it out. You could do what we just did, which is get a ruler and measure it. Hopefully, if you could do that now if you haven't done it already. Or you can use beautiful, beautiful maths. So if you're measuring this line on your bit of paper, the ant's displacement, then you should have got a number sort of, well, I've put on the PowerPoint 21.6. In reality now I get 21.7, but like I say, that's okay. Well done if you've put it in centimetres not millimetres, because the question did ask for centimetres. That's important in GCSEs. Shall we look at how you use the beautiful, beautiful maths method? Oh, I should say, have you drawn an arrow on it as well? I haven't. Look, this would not get top marks in an exam. So it's a displacement. So I'm not allowed to just draw the line. It was displaced from up there to down there. So it would be displaced in that direction. There, that's better. Right, let's look at how you use maths to work out the same thing. It's just amazing that Pythagoras very long ago worked out, or someone around that time, that you don't have to keep measuring things. You can use maths. So you can work out the lengths of a right-angled triangle. You're okay with what a right angled triangle is, right? A right angle, 90 degrees, any triangle that has got a 90-degree angle in it like this is a right angled triangle. You can work out the lengths of that triangle using Pythagoras' theorem. He's the one that made this up. A squared plus b squared equals c squared. I'm assuming that a lot of you know what this means. I'm going to quickly go through it though. So one of the lines next to the right angled triangle you call A, and one you call B, next to the right angle. It doesn't matter which one of those is which, you could switch them around. But the long sloping side, what we call the hypotenuse of the triangle, is always C, okay? C's got to be the long slopey side, A and B can be whichever ones you want, it doesn't matter. So our ant's journey was a right angled triangle, right? So we can use this Pythagoras' theorem to work out the length of this green line, what the ant's displacement was. So a squared plus b squared equals c squared. It doesn't matter if 21 centimetres is A or 5.4 centimetres is A, but that long slopey edge has got to be C, all right? So I'll say 21 centimetres is A and 5.4 centimetres is B. Let's put in those numbers. So 21 squared plus 5.4 squared is going to equal that length squared. Awesome. Let's see if it works. So 21 squared is 441. 5.4 squared is 29.16, and you add those together and you get 472.16. This is where you've got to be really careful that if you're in a physics exam and the clock is ticking and you're feeling nervous and your palms are sweaty, that you don't end up just writing that as the answer, because that's what c squared is, but we want c. So we have to unsquare c, but if we're going to unsquare c, we need to unsquare the other side as well. So c equals the square root of 470.16, which is 21.7, which is pretty close, isn't it, to what we got when we measured it? Isn't that amazing? Finally, no more scaling buildings with a ruler to measure what that long slopey bit is. What is the problem with both these answers though? So we've measured it, we've got 21.6. We did the maths, we got 21.7. I'm very happy with that. I can see that, but there's some problem with this. What you can see on the screen here. Clue, we were finding displacement. Have you got it? Of course you got it. Displacement is a vector. We haven't said what direction the thing is travelling in. So you need to know how to line up your vectors so that you get the correct direction. The direction in this case, as we've discussed, was going from the starting point of the ant down to the end of the ant's journey. So to resolve vectors, you won't necessarily always have them lined up like this for you, but you've always got to line up the heads and the tails. When I did this lesson on Facebook yesterday, I kind of accidentally fell into using an example of just a cat's head falling through the air. Not even, it was supposed to be a whole cat, and then I couldn't be bothered to draw the whole cat. So I'm just going to stick to tradition and do that again so that you get what the people on Facebook got. For example, if the question was, there's a cat's head falling through the sky and it weighs, so its weight is the force of gravity pulling it down, right? Let's say it weighs 3 newtons, but there's a strong wind blowing from the left to the right. So there's a wind blowing in this direction with a force of, I don't know, 5 newtons. It might be up to you to find out the overall force acting on the cat, the resultant force acting on the cat's head, by adding those vectors together. So you've got to know how to line those vectors up so that your arrow points in the right direction, yeah? So you've got to do them head to tail, line them up head to tail. So the 5 newtons goes there, and head to tail, so the 3 newtons would go down like that, right? And then you can see that the overall resultant force is going to be, if you've turned those into a right angled triangle, that the overall force is going to be pointing from the top left down to the bottom right. Which makes sense, doesn't it? If a cat's head is falling downwards, but it's also being blown to the right, then what the overall force is doing is pulling it downwards and to the right, sort of constantly. Is that okay? I've done that very small for some reason, but so you would line up the vectors in that way, and that would give you the overall force. And it doesn't matter how you line those vectors up, as long as they're head to tail. So what's another way you could do it? You could have started with the 3 newtons pointing downwards, and then done the 5 newtons going across like that. That would be fine, look, because you'd still end up, even though the triangle's the different way around, you'd still end up with the resultant force going from the top left to the bottom right, so that's fine. Right. You're totally ready for this sheet. And on your exam, they'll only ask you about the vector's velocity or force, I believe, so you don't need to worry about acceleration or anything like that. We've been doing it with displacement, but yeah, it works, all of this system works with force or velocity or any vector. So every vector, in fact, every force, every vector can be said to be made of 2 components like this. Here you go. Here's your sheet. So hopefully fairly straightforward. You got 6 examples. I don't know. It's always like a student has drawn some vectors, but they've done things wrong. Spot the mistake. 6 of these are vectors joined up, but some of them are done incorrectly, and some of them have been lined up correctly to show the resultant force. So the dotted lines are the component vectors, we would say, and the resultant force is the solid line. Can you just tell me which ones of these are wrong? And for the ones that are wrong, could you please rearrange the vectors to correct them? How are you doing? I don't feel like that's going to take you very long. I tried to make them as tricksy as I could, but I was really struggling to make them tricksy, to be honest. All right, shall we go through the answers? A was fine, yeah? Did you get that? Beautifully lined up, there you go. From head to tail, and then the resultant force pointing from the tail of one to the head of the other one. Splendid. B, did you get tricked by B? You shouldn't have done, because there's no problem there. That is also perfectly fine. C was not correct. The vectors are lined up head to tail, but the resultant force is going in the wrong direction. So you need to switch that around. D, that is not correct either, is it? Because they're not lined up head to tail, they're just pointing head to head. E was correct, and F was also not correct because the tails are together. So if you were going to correct those, you would use an awesome burning PowerPoint effect to turn that arrow on C around the other way. That's all you need to do. D, you would need to just move those vectors around so that they were head to tail. There we go, like that. And you'd have to do the same with that with F as well. So yeah, just a reminder that it doesn't matter, as long as you point the vectors head to tail, it doesn't matter which way around you do them. So here you go, you can see that these are the same vectors being lined up differently, but you end up with the same overall resultant force. It's like magic. Right. I think you've got all the information that you need to answer these questions to finish the lesson. I've tried to make them as tricky as I could, but actually I've taught this lesson a bit better than I did on Facebook yesterday, so I don't think you're going to find this too difficult if you've understood everything that I've said before, which is the point of these questions, is to check that. So, question number 1. A girl runs 4 kilometres west and then 6 kilometres north. What is her displacement? I've been very kind and drawn you a diagram, because you should always draw a diagram if you get a question like this in an exam. Can you find the answer by drawing a scale diagram on your paper? I'm chuckling a little bit because my child that I did this with didn't understand what a scale drawing was. They just did the calculation. And when I was like, no, you need to draw a diagram, they drew a diagram and still just did a calculation. I'm like, no, don't sketch it, actually draw it, right? So your scale is 1 centimetre equals 1 kilometre. They might ask you to do this in an IGCSE. So you can't just throw Pythagoras' theorem at it, even if you love Pythagoras. You've got to draw out the scale diagram, please, and then actually measure it like we did with the ant example. And B, can you then calculate the answer using a squared plus b squared equals c squared and see if you get the same answer? Question number 1, 2. If she runs at 4 metres per second west and then 6 metres per second north, what is her resultant velocity? And question number 2. Wormy's parachute. This is good revision for forces, because I think some of you are going to be a bit confused by this, but if you've watched my terminal velocity lesson, this does make sense. Wormy's parachute opens, producing an upwards force of 10 newtons. Wormy weighs 2 newtons. A wind is blowing with a force of 11 newtons from the left. What's the resultant force acting on Wormy? Right, I've said them all out loud. I'm going to do these with you, and when I have finished them, then we will go through the answers. So I did say that you needed a calculator. Sorry, the question came up on Facebook yesterday. You will get you won't get one. You can take a calculator to an IGCSE Physics exam. In fact, you absolutely definitely should do. Please do. Do not go into your exam without a calculator. You will need one. right, I have written mine down, so I'm going to go through it. Hopefully if you're not quiet at the end, then you can follow along with me. Question number 1. A girl runs 4 kilometres west and then 6 kilometres north. What is her displacement? Find an answer by drawing a scale diagram on your piece of paper. Oh, how I wish I'd used a pencil. So I drew this diagram. What mistakes have I made, please? Come on. What mistakes have I made? You should be able to spot quite a few, actually. I've drawn a line and written 6 kilometres, bracket 6 centimetres. I've drawn another line up saying 4 kilometres, 4 centimetres. And I've written displacement equals 4.7 kilometres because I've measured it. I just drew a little arrow to my sad face because if I used a pencil I could have rubbed it out and started again, and I couldn't. I went a bit wrong with my line and they don't quite join up. I haven't put any direction on, have I? I haven't. So she runs to the west and then she runs to the north. That's better. I mean, really, I suppose I should have put the arrow at the top there. So now they're vectors at least, and I can see that this is the displacement goes from the bottom right up to the top left like that. So I could show on my sketch. That would probably be enough to get me a mark showing that I knew the direction. So I knew that I was a bit off because of this mistake here. If I'd been in an exam, I would have tried to do that again. Be careful that you write kilometres, yeah, and not centimetres, because you want to give the answer. You don't want to give the measurement, if you see what I mean. So let's do it with Pythagoras then. I said that the 6 was A and the 4 was B. It doesn't matter which is which, and the displacement has to be C. So 6 squared plus 4 squared equals C squared. So 6 squared is 36, 4 squared is 16, and both those added together equal C squared. So you end up with C squared equals 52. So C equals the square root of 52, which equals 7.2. And again, I thought, oh, just double check, look at the question. Careful that you don't write centimetres. It's not centimetres, it's kilometres. And what else have I got to do? Because it's a displacement. It's a vector. So I need to add a direction to my answer. What am I going to say? Well, the question kind of tells me, doesn't it? She's running northwest. There we go. The resultant velocity, well, did you get that if she's running exactly the same, but just the units are different, then the resultant velocity is going to be exactly the same number, but with different units, yeah? Because it's exactly the same triangle. So her resultant velocity was going to be 7.2. Be just really careful with the units. Metres per second, because they gave you metres per second in the question. And this one, did you get this? So first of all, you had to know, it was deliberately trying to get you really confused. You had to know that things that are slowing down in the downwards direction can still have a resultant force acting on them in the upwards direction. Do you remember that? So Wormy's travelling downwards. She opens her parachute. Suddenly there's a really big force acting upwards, but she's moving downwards. So what happens is she doesn't start to move up. She slows down in the downwards direction. Yeah? So that was sort of there to deliberately confuse you. So I just drew out the diagram, and then you can sort of hopefully quite quickly in your head work out the vectors going up and down. So if there's a 10 Newton force pushing her up and 2 Newton force pulling her down because that's her weight, then that overall force is 8 Newtons in the upwards direction. So I put that on a little sketch. And the, oh no, put it in the, oh no, look what I've done. Oh my goodness, brilliant, classic error. So I didn't draw the arrows on when I was doing my sketch. And I've fallen into the exact trap of thinking, oh, she's parachuting, so the resultant force is going to be downwards. No! Oh, I'm actually really pleased that I did that. So if I'd done the sketch and I'd drawn the vectors while I was doing the sketch, I wouldn't have made that mistake. So it's 8 Newtons upwards. And then I can see that it's 11 Newtons across, but I need to do head to tail, don't I? So the 11 Newtons is going to be in that direction. So my number's okay, but my direction is incorrect. I wouldn't get a mark for that because I've shown the direction as being going down, and it's not. The resultant force is acting upwards. This would actually be a brilliant IGCSE question. So yeah, the overall resultant force is going to be acting in the upwards direction, even though she's falling down. Don't be confused, that's fine. And then, luckily, so this is still C. So I still have 8 squared plus 11 squared is going to equal this C squared. So my C squared is 64 plus 121, which is 185. So I square root that to get C. And the answer was 13.6. And again, I left the units off because I would always double check the question before I wrote my units on. And we're looking at force this time. So it is newtons. Whew. And that makes sense because force is a vector. Thank you for joining me for this exceedingly unfestive final lesson of our IGCSE Physics Force and Motion lesson. I hope that you enjoyed it. Over on my website, It's actually in the archive section at the moment, but there is a lesson just called The Maths. So if you're a bit unclear on things like rounding or significant figures, which it's sort of more A-level stuff, they tend to kind of let you get away with it at IGCSE, but if you want to polish up your maths a bit, the maths that will be relevant to this module, then do go over to my archive bit and watch my lesson on there. Right, I'm going to go over to my Facebook page, as I always do when I'm live on YouTube, just in case anyone has left me any comments on the top Facebook post pointing you into the direction of this lesson. Yes, thank you very much for joining me, and that is the end. I'm going to go off on my Christmas break, so it's up to you if you want to watch. Well, I'm not going to go off on my Christmas break, I'm going to set you some homework like I always do. But I won't be teaching alive next week, so if you want to watch that maths lesson, then you can. It was actually pre-recorded. I don't usually do that. It took me so long. I haven't watched it back for ages. I'm wearing like different clothes at different points because it like literally got dark and I went to bed and then I got up. This is why I can't pre-record lessons. But anyway, it took me ages. Oh, hello, Gus! Yes, he's actually watching live this Wednesday. It's Gus! Gus, what do we call you? In our all ages lessons, Gus has many names. When we did all ages lesson on fungus, Gus was called Fun Gus. Now we've been doing the human body, he's Osophagus, yeah? But yeah, we haven't worked it out, have we, Gus, for these IGCSE Physics lessons. Gus of wind, it's not the same. Oh, hello, Bastian! And Tiger and Bird and Banjo are here. Oh, lovely. Look at that. The core crew. Thank you very much, by the way, if you've been lurking this whole time on YouTube and you haven't left me a comment on my Facebook page. I also really appreciate you watching as well. And if you're watching on catch-up, I appreciate you equally as much as I just appreciate you, yeah? I just really appreciate you. Thanks, guys. If you want to support me, please, by all means, do go to my About section and sign up for Theatre Science Magazine, which will be coming to my existing supporters in January, because that's what I keep saying, and if I keep saying it, then it will happen. But you will, if you sign up now, get a past issue, which you can read straight away to tide you over. Thank you. See you all next time. Bye.